Hello everyone, my name is Christian Faria, and today I will be presenting the X-ray diffraction characterization of yttria-stabilized zirconia for use in a solid oxide fuel cell. So to give an overview of the topics I'll be covering today, I'll start out with a brief introduction to X-ray diffraction, what that means, and how it's performed, followed by X-ray diffraction of ceramics in particular, and the application of zirconia as an electrolyte material in the use of a direct carbon fuel cell, which is the subject of my thesis research. Getting into the bulk of this presentation, I will be discussing how to perform X-ray diffraction on this zirconia electrolyte, starting with its preparation, followed by the measurement of the values through X-ray diffraction, the characterization of the data obtained, microstrain present in the material, and some alternate methods to verify our findings from X-ray diffraction. And then I'll wrap it all up showing how the X-ray diffraction data will tell us information about how this electrolyte will perform when it's put into use in a fuel cell. So we all know that light is a form of electromagnetic radiation that propagates as waves. And these waves are so-called that because they have an electric and a magnetic component, as shown in the top right-hand side of this slide. So X-rays differ from, for example, visible light because their wavelength is much shorter and they therefore have a higher frequency. So the frequency of the wavelength of X-rays is anywhere between 0.02 and 100 angstroms, whereas for visible light it's around 4,000 to 7,000 angstroms. So this means that X-rays are useful for diffraction of crystallographic materials because their wavelength can fit into the spacings between the crystallographic planes in a material, whereas something like visible light has far too long of a wavelength to fit into that small length there. So what exactly is diffraction? Well, this image on the right side of the screen here, I want you to imagine you're looking down at a calm lake with no waves at all. Then these two silver rectangles there are creating disturbances in the surface of that water. And as they create disturbances, waves show up in the surface, they propagate radially. Now, as they interact with one another, they can create constructive or destructive interference. Now, this interference is defined as diffraction. The destructive interference occurs when the waves cancel each other out, and you can see that in those lines kind of radiating out in between the thick blue and black bands there. Whereas constructive interference is the larger lines showing the blue and the black stripes as they combine and move outwards from the source. So the diffraction peaks produced by constructive interference from the X-ray beams at specific angles give us the values that we use in X-ray diffraction data. So how do we get X-rays? Well, there's three main ingredients. There's a high accelerating voltage, a source of electrons, and a metal target, and that creates X-rays. So looking at an X-ray diffraction apparatus here, we have the X-ray tube on the left, which creates the X-ray waves that are then focused down on a sample. They reflect off and they're picked up by a detector on the other side. Now you'll notice this dashed line circle there. Really the X-ray tube and the detector can rotate around the sample, and that allows a wide range of angles to be obtained from the sample. So as it moves around, it picks up all of the crystallographic planes at any angle that could be within the sample. So if we zoom in a little bit on the sample, we can take a look at what's happening as these X-ray beams actually interact with a crystalline material. The incident beam coming in from the left from the X-ray tube hits off the certain planes at very specific angles called an angle of incidence. When it reflects off of that, the reflected beam is then picked up by the detector, and the data obtained through this angle, as it's constantly changing, as the X-ray tube and the detector are moving around the center sample, gives us our diffraction data. And the correlation between the X-ray wavelength, the D-spacing, which is the spacing between the crystallographic planes, and the angle is called Bragg's law. So when we know the wavelength of the X-ray beam, for example, and we know the angle, we can determine the D-spacing through this relation. So when we plot the intensity of X-ray waves going into the detector as they sweep through that entire angle, we can obtain this X-ray diffraction pattern, or diffractogram as it's sometimes called. And the location of the peaks on this plot correspond to the crystallographic angles, the crystallographic planes rather, within the sample. So from this information we can determine the D-spacing through Bragg's law, and with that D-spacing we can then determine what plane we're looking at and what the lattice parameter of that specific structure is through a certain relation. So for a cubic structure, it's this relation. For other structures, the formula changes. And moving on to ceramics, William Kingery, who's regarded as the father of modern ceramics, defined a ceramic as a non-metallic inorganic solid. And that's a very broad definition, but it is comprehensive. So the goal of X-ray diffraction is to determine the atomic structure of a material. And to this point, fundamentally, we want to know, is the material crystalline or is it amorphous? And what impact does that have on the actual X-ray diffraction pattern? So if we look at the top of this plot here, we see it's not very well defined, it's very broad, and that corresponds to an amorphous material. There's no long-range order, so there's no well-defined peaks that tell us where any crystallographic planes are because they don't exist in that material. Whereas if we look at the lower part of this plot, we see very well-defined diffraction peaks, which correlate to a crystalline material, because as the angle sweeps, it goes through and reflects, the X-ray reflects off all of the crystallographic planes within that sample. So to perform X-ray diffraction on ceramics requires the use of nanoparticles. This is because there are fewer lattice planes in nanoparticles as opposed to microparticles, for example. These fewer lattice planes reduce the destructive interference from other amorphous phases that could exist in microparticles. So ceramics require thermal processing, and there's also in situ XRD analysis that can be done called high temperature X-ray diffraction to simulate exactly what is going on in the ceramic material as it is centered and as it goes through those temperature changes. So the application of zirconia as an electrolyte to my thesis research can be found in this slide here. I'm working in Professor Adam Powell's Energy Metals Research Group to develop a direct carbon fuel cell which combines solid carbon fuel with oxygen gas to yield CO2. Now, this reaction results in CO2, which is a greenhouse gas, and of course, it's not exactly the best for the environment. However, the advantage of this device is that there's low entropy, very low entropy, of the carbon plus oxygen to yield CO2 reaction. And theoretically, there's 100% efficiency that's possible. Now, this device won't be operating at 100% efficiency. We forecast it'll be around 70% due to thermal and other losses within the cell itself. But when you consider gas turbines, conventional gas turbines, they're only operating between 50 to 60% efficiency. So this fuel cell has the potential to use carbon fuels such as biomass or coal and gain electrical energy, transmit electrical energy from that reaction in a much more efficient manner. So if we zoom in on a certain aspect of this overall fuel cell design here, we see that there are three key components to any fuel cell. There's a cathode, an anode, and an electrolyte to facilitate ion exchange between the cathode and the anode. Now, the dense electrolyte is what's made from zirconia. And we selected zirconia for this material because it has high chemical stability in reducing or oxidizing environments, and it's very selective to the diffusion of oxygen ions between the anode and the cathode. So in the image on this screen here, you can see this is actually a yttria stabilized zirconia tube that we'll be using in our experimental apparatus. And you can see that the zirconia is a white crystalline material, and it is actually stabilized with yttria. The reason for doing that is yttria prevents zirconia from going through a change in its atomic structure as temperature changes. Pure zirconia is, there's three main structures of it. There's monoclinic, tetragonal, and cubic. And as temperature varies, these phases can change. So at room temperature, it's monoclinic. At around 1200 Celsius, it transforms to tetragonal, and then around 2400 Celsius, it transforms to cubic. So adding yttria to zirconia prevents it from making these violent changes. It's still possible to occur, but it stabilizes it much more, improves the thermal, mechanical, and electrical properties. And it really doesn't require too much yttria to do this. Anywhere from 2 to 12% will stabilize the zirconia and make it a much more useful material for this application. And we can see that the general structure of zirconia is a fluorite structure. It has zirconium atoms at the sites of the FCC structure with oxygen atoms at the 8 tetrahedral interstitial sites. So our desired properties for this in a solid oxide fuel cell show we want to have a thin layer of this only, because a thick layer will contribute to the resistance of the oxygen ions diffusing through this material. And that'll contribute to our overall losses. We want to keep the efficiency of this cell high, so we want to reduce the thickness of the electrolyte as much as possible. So in forming these electrolyte tubes, we have to be mindful of what the processing requires and what the grain size is of the zirconia, of the YSZ, the yttria stabilized zirconia, in this actual electrolyte. So there are three main methods of oxygen ion transfer through the YSZ. There's grain transfer, grain boundary transfer, and a combination of the two. And we'll revisit this image later after we have performed our characterization via X-ray diffraction. So moving on to how to actually take X-ray diffraction of the YSZ electrolyte, it starts with microcrystalline powders, which are then ground in a planetary mill. You can see the planetary mill contains these small chambers full of other YSZ balls that, as it rotates around its own axis and then the axis of the center of the apparatus, these balls grind up the microcrystalline powder and create a nanocrystalline powder. And as mentioned before, the nanocrystalline powder is much better for X-ray diffraction because there's less interference from amorphous phases. So after this powder is collected, it's sintered into samples, into discs, or it can be tape cast or gel cast into a film adobe and then cut out and placed in the X-ray diffractometer for measurements. And we've got some SEM images here showing the different grain sizes from the different sintering processes. And here's an image of the YSZ nanoparticles. You can see they're about 80 nanometers in diameter. So the particle grain size can be determined by three primary ways. There's X-ray diffraction, which is the most accessible, we can say, and it really provides the information we want to know about the average grain size, and it also tells us about the microstrain present in the material. Scanning electron microscopy can also work, but its resolution is usually on the micro scale rather than the nanoscale. To get down to the nanoscale requires a transmission electron microscope, which requires elaborate sample preparation, but it does have a very fine resolution that's possible. So in using X-ray diffraction, there are a few methods to determine the crystal size. There's the Scherer relation, there's the Williamson-Hall method, and the Warren-Averbach method, which is based on a Fourier series to fit the X-ray diffraction data on that plot. So here we have an image of the diffraction peaks of YSZ after performing X-ray diffraction. So the bottom curve here, you can see this is just a green ceramic with 10% yttria in this zirconia. And you can see the peaks are not very tall and they're rather broad. But as the sintering increases, you can see the next three lines, they're sintering at 750 Celsius, sintering at 850, and sintering at 950 Celsius. And as the sintering temperature increases, the peaks become more well-defined, they're less broad, and they're taller. And the reason for that is, as the sintering temperature increases, there's an increase in grain growth and a decrease in the peak width due to a decrease in the amorphous-like phase, it's referred to. So looking at the data from this X-ray diffraction plot, we can see that the Scherer relation obtains a reasonable estimation of the grain size, but really it's an underestimate compared to the other two methods. And the reason for that is it neglects the strain contributions to the observed peak broadening, whereas the Williamson-Hall method and the Warren-Auerbach method both take that into account. And if you're wondering what the dA and dV stand for here, dA is the area weighted grain size, and dV is the volume weighted grain size. Further, we can perform a Rayet refinement, which provides microstructural analysis from the X-ray diffraction data, and it does that by utilization of software such as FullProf, which provides the information on the lattice parameter of a certain material. So in this particular case, we can see that the A dimension of the lattice is about 3.63 angstroms, and the C dimension is about 5.14. So since the A and C are not equal, this isn't a cubic structure, this is actually a tetragonal structure. The image on the right here shows a cubic structure, but it was included here just to show how selective the yttria stabilized zirconia is to oxygen ion conductivity within the grain. So you can see how the oxygen ions move through that lattice by vacancy transfer. Moving on to the Williamson-Hall plot, you can see that a plot of the broadening versus the sine theta results in these linear relations here. We fit a curve to the line, and that allows one to see the slope, which correlates to the strain in the lattice, and also the y-intercept, which correlates to the grain size. Now, you'll see that the microstrain is reduced as the sintering temperature increases, until up to 950 Celsius, where in this particular case, it's the authors referred to it as an unphysical shape. So that data is a little off, but in general, the strain decreases as the sintering temperature increases. Looking at an image of the grains on a SEM, we can see that it's difficult to tell the grain size on this. The resolution isn't great, so we can move on to a transmission electron image here. And I really like this image. It's so cool to see this at this scale, and I'm just so impressed by it. It shows the zirconium atoms here looking down at the 100 plane. So the yellow highlighted parts here are zirconium atoms, and the white ones are oxygen atoms in that lattice. Finally, impedance spectroscopy can be performed on the YSZ samples, and that measures the resistance and capacitance properties of a material. So you can see that the intergranular resistance is reduced as sintering time and temperature increases, and the density of the electrolyte increases as the sintering time increases. So in conclusion, X-ray diffraction of a YSZ electrolyte reveals key parameters affecting the SOFC performance. And the crystal size can be determined primarily by X-ray diffraction. That's probably the best overall way to do it, but SEM or TEM images can also tell us the grain size. The multi-step sintering results in the smallest grains, and the electrolyte density increases with sintering temperature. Now, crystal size can dictate ion conductivity. This is the image we showed before. It shows that there's the 3 modes of ion transfer within the electrolyte, and nanocrystalline grains have better grain boundary conductivity by 1 to 2 orders of magnitude when compared to the microcrystalline grains. The microstrain can be determined from the Williamson-Hall plot, as we saw, and impurities and the material composition are very evident on the X-ray diffraction plot. They'll show up as a more broad plot rather than the well-defined peaks that we'd like to see. So in sum, X-ray diffraction of this electrolyte allows us to determine its suitability in a fuel cell before operation. Thank you for your time, and I look forward to reading the comments below.